Hi, this is Dr. Hayek, and today's video is about electrochemistry. Now, before I start my video, I would like to represent the outline of this chapter, where I'm going to talk about all the topics, and please refer to this page when you want to search for your topic of interest and click on the corresponding video to watch it. Electricity is very important in our daily life, and more importantly, if we can carry it around with us, and hence the role of batteries. Now, batteries, in every electronic device, you can find a battery that varies in size according to the need. Take, for example, the car battery, which has a larger size compared to the watch battery. Today, I will be talking about how a battery works and what is it made from. But before that, let's discuss the redox reaction. Redox reaction is the sum of two half equations, the oxidation and the reduction. In this example, I'm showing the oxidation of zinc, where zinc is losing 2 electrons, and the reduction of copper 2, that's gaining the electrons lost by zinc. And therefore, you have transfer of electrons between zinc and copper. The transfer of electrons between zinc and copper can be used in a battery to generate electricity. And instead of having this transfer happening in one solution, we can split the reactants into two solutions, as is represented in the following galvanic, or what's sometimes called voltaic cell. Now the question is, how can we prepare a galvanic cell? To prepare a galvanic cell, you will need one compartment for the anode, another compartment for the cathode. We will use 2 electrodes, for example, 1 aluminum and 1 lead, and a voltmeter that's going to help us measure the cell potential. And we will fill each compartment with the corresponding solution, with aluminum and lead. Now, as you can see in here, the voltmeter reads 0. In reality, the battery will start working and then it will stop after a short period of time. So why this is happening? Because the battery is missing a very essential element, which is the salt bridge. Now, the salt bridge contains a gel of an ionic compound that assures the neutrality of each compartment. Maybe this is not clear. Let's take a look on the following example. The anode compartment is becoming more positive, and the cathode compartment is becoming more negative. And the positive charge of the anode compartment will attract the electrons and therefore will prohibit the electrons from getting transferred to the cathode. And hence the role of the salt bridge. The salt bridge will be pumping negative ions or anions to the anode compartment and positive ions or cations to the cathode compartment. And this way, both compartments will remain neutral at all time. And this will help the battery to continue generating power until that it reaches equilibrium. The salt bridge can be substituted by a porous disc. The porous disc will allow to transfer the extra negative ions in the cathode to the anode. And in this way, also the two compartments will remain neutral at all time. Hi, this is Dr. Hayek, and this video is about electrochemistry, and today we will be talking about the standard reduction potential. In my last video, I have introduced the galvanic cell and how can we build one. Please check the link in the description below to see this video. Once we build the galvanic cell, the remaining question is, how can we calculate the cell potential? Before answering this question, we need to discuss the standard reduction potential of half equations. As you know, the redox reaction is the sum of two half equations, the oxidation and the reduction, and the cell potential is the potential energy of this reaction. If we can determine the standard reduction potential of each half equation, it will be easy later on to calculate the cell potential from the potential energy of the redox reaction. However, there is no way to calculate the standard reduction potential of half equations individually. Therefore, we will need a starting point and a reference. Consider the following galvanic cell, where zinc is at the anode and hydrogen is at the cathode. Zinc is getting oxidized and therefore is losing electrons, and the electrons are being transferred to the hydrogen at the cathode, and hydrogen is getting reduced. Every 2 hydrogen ions will take 2 electrons to form hydrogen gas, which will escape the solution. The voltmeter is indicating a cell potential of 0.76. If we assume that the standard reduction potential of hydrogen is equal to 0, therefore the standard reduction potential of zinc is going to be equal to the negative of 0.76, and the sum of both standard reduction potential will give us the cell potential. In a similar way, we can determine the standard reduction potential of other half equations, as you can see it in the following table. So now, do you know how to calculate the cell potential of this galvanic cell? Take the corresponding half equations from the table, then flip the aluminum half equation because it's an oxidation and it's happening at the anode. And when we flip the half equation, we flip the sign, or we reverse the sign of the standard reduction potential. Therefore, it's negative E0 is equal to 1.66. Now, to sum these two half equations, as you know from balancing a redox reaction, we need to multiply by two integers. We need to multiply by 2, the half equation of aluminum, and by 3, the half equation of lead. And a very important remark is that when you multiply the half equation by an integer, you do not touch the standard reduction potential. After that, when you find the redox reaction, you sum the two standard reduction potentials, and therefore you get the 1.53, which is the cell potential. Once a galvanic cell is built, we can describe it using what is called line notation. Now, the line notation, we started by writing the anode to the far left, the cathode to the far right, and then with two lines in the middle that will represent the salt bridge or the porous disk. Now, between the electrodes and the solution, we put two lines, and therefore, since aluminum is getting oxidized into aluminum 3+, so we put a line between aluminum and aluminum 3+, and lead is getting reduced to lead solid, and there is a line in between these two. Here's another example where a non-metal is used in a galvanic cell. We can describe this cell using the following line notation. The anode to the far left, the cathode to the far right, and then the two lines that will represent the salt bridge or the porous disk. Now, zinc is getting oxidized into zinc 2+. However, here we have used an inert metal as a cathode, and therefore now we separate the solution, which is the H+, and hydrogen gas by a comma, and we write it this way. So H+ is getting reduced into H2 gas. We can also indicate the concentration and the pressure in the line notation, as you can see it in the following example. Hi, this is Dr. Hayek, and this video is about electrochemistry. Today we will talk about the relationship between the cell potential, electrical work, and free energy. Check my previous video on how to calculate the standard cell reduction potential. I will post a link in the description below. Today we will explore the relationship between thermodynamics and electrochemistry. The work that can be accomplished when electrons are transferred through a wire depends on the thermodynamic driving force. This driving force is defined in terms of potential difference between 2 points on the circuit, and therefore the electromotive force is going to be equal to the potential energy, which is equal to a joule of work per a coulomb of charge. Now here we'll consider the cell as the system, and since the work is done by the cell, it will be indicated by a negative sign, and therefore the potential energy is going to be equal to minus W over Q. If we rearrange this expression, we will get that the work is equal to minus Q multiplied by E max. From this equation, it could be seen that the maximum work could be obtained at the maximum cell potential, and therefore W max is equal to minus Q E max. It's noteworthy to mention that we can never realize the maximum work from a cell because of the wasted energy through frictional heating when a current flows. However, we can measure the maximum cell potential using an efficient digital voltmeter. The charge can be calculated by knowing the amount of electrons or number of mole of electrons passing through the wire and using Faraday's constant. And therefore, Q is equal to number of mole electrons multiplied by Faraday's constant. Faraday's law states that the charge of 1 mole electron is equal to 96,485 coulombs. And therefore, we have what we call F, which is the Faraday's constant. It's equal to 96,485 coulombs per mole electron. And now we can relate the potential of a galvanic cell to the free energy. We know that for a process at constant temperature and pressure, the change on free energy is equal to the maximum of useful work, and therefore delta G is equal to the work maximum. And we know that the work maximum is equal to minus Q times the cell potential. And we know that Q is equal to number of mole electrons multiplied by Faraday's law. So if we put all this together, we will have that the change of free energy, it's equal to minus number of mole electrons multiplied by Faraday's constant multiplied by the maximum cell potential. For standard conditions, delta G0 is going to be equal to negative number of mole electrons multiplied by Faraday's constant multiplied by the standard cell potential. Now, we know that for spontaneous processes, delta G has to be negative. And since delta G from this expression is proportional to the negative of cell potential, so we can tell that the galvanic cell will always run in the direction that gives positive cell potential. Hi, this is Dr. Hayek, and this video is about electrochemistry, and today we will talk about concentration cell and the Nernst equation. So far, we have described cells under standard conditions. Today, we will discuss the dependence of cell potential on concentration. Consider the following redox reaction for a galvanic cell at standard conditions, where you have zinc at the anode and copper at the cathode, and the standard cell potential is 1.10 volt. According to Le Chatelier's principle, if we increase the concentration of Cu2+, the reaction will favor the forward direction, and therefore the cell potential will increase. However, if we increase the concentration of Zn2+, which is a product, the reaction will favor the reverse direction, and therefore the cell potential will decrease. A concentration cell is prepared the same way as a galvanic cell. By definition, a cell in which both compartments contain the same component but at different concentrations is called a concentration cell. In the cell described here, the concentrations of nickel in both compartments are 1 molar and 1.0 times 10 to the power minus 3 molar. The question now, in which direction will the electrons flow in this cell? The best way to answer this question is to think that nature will recognize to equalize both concentrations in both compartments. Therefore, the electrons will flow from the less concentrated compartment to the more concentrated compartment. If the cell had 1 molar concentrations in both compartments, the standard cell potential will be equal to 0, since both compartments they have the same half equation. So the question now is, how can we calculate the cell potential of this concentration cell? Before answering this question, we need to discuss first the Nernst equation. The dependence of the cell potential on concentration results directly from the dependence of free energy on concentration. Recall from thermodynamics, delta G is equal to delta G0 plus RT ln of Q. And we have discussed previously that the change on free energy is equal to minus NFE. And at standard conditions, delta G0 is equal to minus NFE0. The equation then becomes minus NFE cell is equal to minus NFE0 cell plus RT ln of Q. If we divide both sides by minus NF, the equation becomes E cell is equal to E0 cell minus RT divided by NF ln of Q. At 25 degrees Celsius, this equation can be modified to give E cell is equal to E0 cell minus 0.0591 divided by N log of Q. The 0.0591 value is coming from replacing R, T, and F by their values. The 2.303 number is coming from conversion of natural log to log base of 10. Using nearest equation now, we can calculate the cell potential, where Q is equal to the concentration of nickel at the anode divided by the concentration of nickel at the cathode. Replacing these concentrations by their initial values, the 1 molar and the 1.0 times 10 to the power minus 3 molar, this will give us the cell potential, which is equal to 0.089 volt. At equilibrium, where both concentrations are equal, the cell potential will be equal to 0. Now, in general, the equilibrium constant could be calculated from the nearest equation. We know that at equilibrium, E cell is equal to 0 and Q is equal to K. Replacing these two terms in their values in the nearest equation, we get 0 is equal to E0 cell minus 0.0591 divided by n log of K. Rearranging this expression, we get that K is equal to 10 to the power n multiplied by E0 cell divided by 0.0591. This is Dr. Hayek, and this video is about electrochemistry. Today we will talk about the stoichiometry of a galvanic cell. Please check my previous videos related to electrochemistry. I will post the links in the description below. Consider the following galvanic cell. We are operating here at standard conditions since the concentrations of aluminum and lead are equal to 1 molar. As you can see, the 1 molar concentration is represented by 4 particles in each compartment. Today we will study the stoichiometry of a galvanic cell using particulate representation. Since the oxidation is happening at the anode, so more aluminum ions will be generated in the solution, and the aluminum electrode will decrease in mass since more particles are leaving the electrode. Since the reduction is happening at the cathode, the number of particles in solution will decrease since more particles are getting deposited on the cathode, and therefore the mass of the cathode will increase. As you can see, 2 particles of aluminum 3+ were released in the solution, and the charge of the anode compartment was increased by 6+, and this will lead the cell to stop since the anode compartment is getting positively charged. The salt bridge will pump anions into the anode compartment. Since every anion has 1 negative charge, then a total of 6 anions will be added to the solution. In a similar way, 3 particles of Pp2+ were deposited on the cathode, and therefore the charge of the cathode compartment was decreased by 6+. Then the salt bridge will pump 6 cations into the cathode compartment, since every cation has 1 positive charge. Let's review the overall process now. 2 aluminum particles will be generated in the solution, increasing the charge of the anode compartment by 6+, and 3 lead 2+ particles will be deposited on the cathode, decreasing the cathode compartment charge by 6+. The salt bridge will pump 6 anions of 1 negative charge each to the anode compartment and will pump 6 cations of 1 positive charge each to the cathode compartment. This way, both compartments will remain neutral and the cell will continue generating power. Let's remember now the redox reaction in this cell. You can go back to my previous video on standard reduction potential to review how to calculate the standard cell potential. The question now is, what happens to the cell potential when the cell operates enough time for the concentration of aluminum 3+ to change by 0.5 molar? To answer this question, we will be using ICE table. Initially, both concentrations are equal to 1 molar. If the concentration of aluminum 3+ will change by 0.5 molar. This means it will increase by 0.5 molar since aluminum 3 plus is a product. Therefore, the concentration of lead 2 plus will decrease by minus 3/2 multiplied by 0.5. Now the 3/2 is the molar ratio between lead 2 plus and aluminum 3 plus. At the end, the total concentration will be 1.5 molar for aluminum, 0.25 molar for lead. To calculate the cell potential now, we use the Nernst equation, where Q is equal to the concentration of aluminum 3 plus squared divided by the concentration of lead 2 plus cubic. Substituting every term by its value, then we get the cell potential is equal to 1.51 volts. To explain the particulate representation, we can use ice table as well. Initially, we had 4 particles of each. Since 1 molar corresponds to 4 particles, the change by 0.5 molar will correspond to 2 particles. Therefore, the number of particles of aluminum 3 plus will increase by 2 particles, and the number of particles of lead 2 plus will decrease by minus 3/2 multiplied by 2 particles. I remind you again that 3/2 is the molar ratio between lead and aluminum. At the end, we will have 6 particles for aluminum and 1 particle for lead. So initially, we had 4 particles in each compartment, and the cell potential was 1.53. At the end, we will have 6 particles of aluminum, 1 particle of lead, and the cell potential is equal to 1.51 volts. Hi, this is Dr. Hayek, and this video is about electrochemistry, and today we will talk about electrolysis, electrolytic cell, and electroplating. This is going to be the last video on the series of electrochemistry, so please check my previous videos. I will post the links in the description below. A galvanic cell produces current when oxidation-reduction reaction proceeds spontaneously. A similar apparatus, which is called electrolytic cell, uses electrical energy to produce chemical change. The process of electrolysis involves forcing electrons into a cell to produce a chemical change for which the cell potential is negative, which will cause a non-spontaneous reaction to occur. Consider the following reaction between zinc and copper. The cell potential is 1.10 volt, which is positive. So this redox reaction will proceed spontaneously in the forward direction, and therefore it will form a galvanic cell. If we were to force this reaction to proceed in the reverse direction, we have to apply a potential which is greater than 1.10. The power source with a voltage greater than 1.10 will force the electrons to flow in the opposite direction. Notice that since the flow of electrons is opposite in the 2 cells, the anode and the cathode are reversed as well. Also, the flow of ions in the salt bridge will be reversed as well. Electrolysis has great practical importance. For example, charging a battery, producing metals from their ores, or plating an object, which is the example that we will see next. Consider the following electrolytic cell where a ring is being plated with copper atoms. Now, the copper electrode represents the anode where the oxidation is happening, and the ring represents the cathode where the reduction is happening. Both they are immersed in a copper 2 solution. As you can see in here, copper ions are being generated from the anode, and they are being reduced at the cathode, which means plated on the surface of the ring. The copper electrode will decrease in mass with time, and the ring will increase in mass with time. Now we will consider the stoichiometry of electrolytic processes. The question is, how much chemical change occurs with the flow of a given current for a specific time? Now suppose we want to measure the mass of copper that was deposited on that ring. We know that at the cathode, the copper is getting reduced, and therefore we have the reduction half equation. We can calculate the amount of charge by multiplying the current intensity, which is in ampere, by the time, which is in second. We know previously that the amount of charge is equal to number of mole electrons multiplied by Faraday's constant, where Faraday's constant is equal to 96,485 coulombs per mole electrons. So from the amount of charge, we can calculate the number of mole electrons. From the half equation that's happening at the cathode, we can determine the number of mole of metal that's being plated on the ring by using the molar ratio between the metal and the electrons. From this expression, we can calculate the number of mole of metal that was deposited on the ring. Using the number of mole and the atomic mass of the metal, we can calculate the mass of metal that was deposited on the ring. So let's review this. If we have current and time, we can calculate the amount of charge applied. From the amount of charge applied, which is in coulombs, we can determine the mole of electrons that passed through the cell. From the number of mole of electrons, we can determine the number of mole of copper. And you all know from the number of mole of copper, by multiplying it by the molar mass, we can determine the grams of copper that was plated on the ring. Let's take another example of electrolytic cell, which is hydrolysis or electrolysis of water. We know that hydrogen and oxygen will combine spontaneously to form water. The free energy released can be used in a fuel cell to produce electricity. As you can see from the two half equations, the cell potential of the redox reaction using water is going to be negative. When a potential greater than 2.06 volts is applied to water containing enough ions for a current to flow, an immediate evolution of bubbles of hydrogen and oxygen will be observed. Note that twice as much hydrogen is produced as oxygen. I hope this video was helpful to you, so please like, share, and subscribe, and I will see you next time.